So this is the example problem that we are going to solve right now. First, let us read the problem statement. It says solid potassium chloride of the flow rate, temperature and pressure has been given, has to be crushed. Now, you have to use the equidistance particle size distribution of mesh type 10 intervals between 0 to 10 millimeter. So that is the mesh size has been given, and a normal distribution function with standard deviation of 1 millimeter and D50 of 5 millimeter has been given. That means it is said that the feed also has a particle size distribution over here. That's what it means. Okay, it is having a normal distribution function with a standard deviation of 1 millimeter and D50 is equal to 5 millimeter. That means 50% of the feed is already there below 5 millimeter. Now we have to crush this feed to a new PSD. So product PSD with D63 and RRSB dispersion parameter of 2 millimeter and 1 respectively. That means 63% of the crushed product will have a diameter which is 2 millimeter or below. That's what it means. From the statement itself, it is clear that RRSB distribution function has been chosen over here. Now, this is a problem of the third category, the simplest category, okay, where we are just specifying the particle size distribution and asking Aspen Plus to perform the simulation for us. We are not specifying any crusher, we are not specifying any comminution laws, anything. The second one is we are specifying the comminution law, the bond work index. The second problem states, crush the feed with power and RRSB dispersion parameter of 2 kilowatt and 1 respectively. Here also the distribution function is RRSB, and here we are setting the power to 2 kilowatt. That means the crusher is operating with a power of 2 kilowatt. So this is the second case, okay? Second type of case where we are setting the comminution power and the distribution function. In the third case, it is gyratory crusher. Here the crusher type has been mentioned. And the outlet particle diameter should not be more than 2 millimeters. So that is also said. And finally, use a ball mill. So this is the last case. Is they use a ball mill and its diameter is 1 foot and it consumes 0.5 kilowatt and it has an efficiency of 75%. It doesn't operate at 100% efficiency as per Bond's law. And here the bond work index has been given and the log normal distribution with 0.5 geometric mean deviation. So that is also specified. So we will solve all these 4 problems one by one. So let us first start with this, the first problem where the PSD, outlet PSD has been specified. For that, let us go to the simulation window. First, we have to go to the properties. In the properties, we have to first specify our material, that is potassium chloride. So we write KCl over here. It will automatically take, but it takes it as a conventional material. That means it will take part in the phase equilibrium. But we do not want that. We want to fix it as a type of solid so that it is considered as solid only. And then go to next. And we have to choose a property method. Let us choose solids and run. Yes, now the solid property method has been run. Now let us go back to our simulation window. Here, first we have to do two things. One is define a stream class. Okay. Mind that this is not a conventional stream class. It is a conventional solid stream class with particle size distribution. So we will choose the stream class which is a conventional solid with particle size distribution. So we have to choose this one. And for that, both the streams will be of this nature. So globally, it is done. And the second thing that we'll do is get the PSD, that is the particle size distribution. Now we come back to our problem statement. Here it is said that the PSD is equidistance of 10 intervals between 0 to 10 millimeter. So it is equidistance 10 intervals from 0 to 10 millimeter. Done. So you create the PSD mesh, created. Now you are ready to feed in the data. So go to feed. Here the data has to be given. What is the feed? Feed is solid potassium chloride. So we do not have any mixed feed, we have solid. And its temperature is 20 degrees centigrade, 1 bar pressure. So it is 20 and 1 bar. And the mass flow rate is 1200 kg per hour. So we choose mass flow, which is 1200. Okay. Now it is not yet ready because we have to give the particle size distribution information of the feed. So when we open it up, it is said use normal distribution function. So you have to choose a distribution function which is normal. Standard deviation is 1 millimeter. So standard deviation is 1 millimeter. And D50 is 5 millimeter. So D50 is 5 millimeter. Now calculate. Okay, so this is the particle size distribution curve. If you see the mass density distribution, you will find a bell-shaped curve, which is expected. So we will expect that after the process is run, our product will be of something like this. So it will not be like this. Okay. It will be at the left hand side. Now let us close it. Feed is specified. Now we are ready to give the specification of the crusher. Now the first case, we are specifying outlet PSD. Okay. So what are the information that we have? The outlet PSD will be having D63 as 2 millimeter and RSB dispersion parameter 1. So this is the new distribution function ID. The distribution function is RRSB. D63 is 2 millimeter, right? It is So RRSB is 2 millimeter, right? 2 millimeter and 1. So it is 2 millimeter and it is 1. And do not forget to give solid only. It's very, very important. Okay. Now it is all specified. You are ready to do the simulation. Simulate, run. So go to the results. This is the result streams. You have feed and product. So obviously there will be no change between feed and product because we are not, the system is not taking part in any phase equilibrium. So there is no change in molar flow rate or entropy, enthalpy, etc. They will be all same. But the particle size distribution will change definitely. So let us see. This is the particle size distribution. Yes. So here you see the feed 0 to 1 millimeter, it was very small. 1 to 2, it is slightly higher. Then 2 to 3, still higher. So between 4 to 5 or 6, 7 millimeters. So entire range of bigger particle sizes were here for feed. But what happens after the crushing exercise? You see the entire thing comes over here. It is shifted. So almost 90% over here. So as we said that it is said that D63 is equal to 2 millimeter that we have set. That means 63.2% of the feed materials, they have come below 2 millimeters. So you can calculate over here 60. If you add these two numbers, it will be around 0.632. Okay. So that's how it is crushed. Now, if you see the particle size distribution of feed and product. So feed and product. Okay, this is in a cumulative mass fraction for only mass fraction. Here you can see this is the feed. Okay, the blue line, it is feed. So the feed line is like this. Now here you can see the entire graph is in semi-logarithmic scale. Okay, this is 0.01. This is 0.001 and this is 0.01. So you may try to change it to linear scale. So for that you have to change its format. So from logarithmic to linear. And minimum, instead of 0.0004, you can place 0. And maximum, obviously, 0.001, 0.01 rather. Okay, in a linear scale, right? So here it is true. So you can now compare the feed and product with more confidence. So this is the feed, right? This is the feed particle size distribution. And we do not have any data over here, but I am sure that you can have a PSD for product of this fashion. So this is left hand side of the feed particle size distribution. Similarly, you can try for other problems. So what is the next problem? Next problem is crushing the feed to particle size distribution with power and RRSB dispersion parameter. So here we have to use a comminution law. Okay. Now we will not delete this one. We shall take another solid crusher. Let us use some other icon. Okay. Now we will use a manipulator, say duplicator manipulator, which can be over here. Okay. And we may reconnect it to this one, and then this material stream comes over here as before, and another material stream may come over here, and this is the product stream of the second crusher. Okay, so let us rename it as product 1 and let us rename it as product 2. Okay, now we have to specify the second crusher. So here only okay. Now first you make it solid only and determine the outlet PSD from comminution power. So let us first go over here and choose the comminution law. We have to choose a comminution law, and what is the criteria? You remember the table? You can refer it. If the particle size diameter is less than 0.05 millimeter, then we use Rittinger's law. If it is over 50 millimeter, then we use Kick's law. But if it is between 0.05 millimeter and 50 millimeter, then we use Bond's law. And our particles, they fall under this Bond's law criteria. Right? So you will use Bond's law. We will use the Bond's law, and bond work index is 10. So we have to give over here Bond's work index 10. Remember, you have to set the bond work index of CL/PSD, not the mix, because there is no mixed flow over here. Now the RRSB dispersion parameter is 1 and power is 2 kilowatts. So you have to set power as 2 kilowatt and RRSB dispersion parameter 1. So the moment you do this, your entire thing is specified. So now it is ready to run. Okay, so it has run very quickly and the results are available. So let us go to the streams. So two products are available, product 1 and product 2. We can directly go to the solid, and then we can see the particle size distribution of feed and two products. And again, like before, you can format it with a linear scale, set it between 0 and 0.01, and you can try mass fraction. Okay, you have taken mass fraction. Again, you have to format it. So this is log scale. So you have to take linear scale, make it 0, and this one is 0.01. Okay. Now, this one is feed. The blue line is feed as before, and green line is for the product one, the first case that we have studied, and the present case that we had studied, it is something like this. Okay, this is the product. So in this case, the first case that we have done, it was not using much of the power, but in this case, the more amount of finer particles will be generated because here we are inducing more power to the crusher. Now let us go to the third case. In the third case, we have to use a gyratory crusher where outlet particle diameter should not be more than 2 millimeters. So very minimum information is there. So while using gyratory crusher, we will try to use the default parameter as much as possible. So let us choose another crusher, gyratory crusher. Let us take this one. So this is the feed for gyratory crusher, and this is the product of gyratory crusher. So rename the product to product 3. Okay. And let us specify the gyratory crusher. The input specification of gyratory crusher we have to feed in. So select equipment, gyratory crusher. Yes. So selection function and breakage function, we do not have any user specified data. So let us use the standard US Bureau of Mines selection function and breakage function. Now only information that has been given to us is the outlet particle diameter should not be more than 2 millimeters. So the maximum particle diameter is 2 millimeters. Okay, and change it to solid only. Then you are set to run the simulation. Do it, and it is run. So again, you can go to the results and check. Let us solve the fourth problem and do it. So the fourth problem is, use a ball mill with 1 feet diameter that consumes 0.5 kilowatt with 75% efficiency as per Bond's law. So the fourth case, let us bring a ball mill. So ball mill looks like, yes, this is the ball mill. And again, we are supplying the feed to the ball mill, and the products coming out. Let us rename it as product 4. Now set the ball mill input parameters. Yeah. So the moment you choose ball mill, the grindability is open, and here also Bond's law, you have to use bond work index of 9 and 75% efficiency. So bond work index of 9 over here, and mechanical efficiency is 0.75. Then specification, ball mill, and you have to use log normal distribution. So here you are not supposed to use RRSB. By default, RRSB comes everywhere. So here they have asked you to use log normal. So use log normal. For that, 0.5 geometric mean deviation has to be chosen. So it is 0.5 geometric mean deviation, and ball mill diameter is 1 feet. So you have to use ball mill diameter 1 feet. What else? Yeah, power specification. So it says 0.5 kilowatt power is required. So you have to give 0.5 kilowatt of power. Let us run it. So you can just go to the results. Yeah, now it is available. This is the streams, and you go at the bottom, CLPSD, PSD, okay. So you have it over here. So these are the results of 4 products, the product 1, product 2, product 3, product 4. Product 1 and 2 we have already discussed, and these are the product 3 and product 4. Product 3 is for gyratory crusher and product 4 is for ball mill. Now, as you can see, the ball mill performance is not that good because it has used only 0.5 kilowatt of power as opposed to 2 kilowatt of power that was used for product 2. And product 3, you can see that there is no fraction of solid above certain range, because here we have set certain maximum particle diameter. So above that, obviously there will be few particles which is above that maximum particle size diameter that has been set, because the majority of particle size will be below that maximum dimension that has been set. Very few particles will be higher than that. Okay. With that, we come to the end of this lecture. I hope you have enjoyed it, and we'll come back with another interesting lecture very soon. Thank you.